So in this video, we are going to learn how to start the homework 3, which is simplifying the control flow graphs, or CFG. So it is the first optimization pass on the KAIST on IR. So I'm going to explain the code line by line a little bit. But for the later optimizations, you may have to come up with your own implementation. So I will not show all the codes for the remaining optimizations. So okay, so the first thing to do for homework 3 is going to this examples folder, and inside this folder you're going to see a simplify CFG folder, and here are a few IR files. So let's look into the first file, which is const prop input, and let's see output at the same time here. So we are having two source code in IR, which is here. One is here and one is here. So our expectation is that you're going to implement the simplified CFG optimization, and inside this simplified CFG there are four sub-optimizations. And the first one is constant propagation of the CFG. So here are a few examples. For example, let's say this block. In this block, you're going to branch depending on the value, and here the value is not doesn't match much. That doesn't doesn't matter much. The important fact is that the then branch and else branch are the same. Regardless of the value of this branching value, you're going to jump to the B1 with an empty argument. So the first optimizations on the simplified CFG on constant propagation is that if you see such a thing, you're going to just replace it with a simple jumping to B1, because you're not going to depend on the value of this branching expression. So we're going to implement a program that converts this line into this line. So here are other examples as well. For example, if the branching value is 1, which is true in KCC, and you can see that actually you are not branching at all. You are always jumping to B1 because it is a true branch, and it is the case. So you're going to translate this program into this program, which unconditionally jump to the B1. So this is equivalent to this, thanks to the constant value of this branching expression. So we replace this branch with this branch. So this is the second micro optimization you need to implement for the simplified CFG. A similar thing happens for this as well. If the branching expression is false, you're going to just ignore the true branch and you're going to directly jump to the else branch. So your optimization should transform this line into this line. And you can do a similar thing for switch cases as well. For example, if you're switching a value but its value is constant, then let me say it this way. So in this example, in this switch case, you're going to jump to B1 regardless of the value of this. So you're going to jump to B1 if the value is neither 2 nor 3. If the value is true, you're going to jump to B1. If the value is 3, you're going to jump to B1. So regardless of the value, you're going to jump to B1. So we are going to replace the entire switch exit with just a plain jumping to B1. Similarly, if you know the value that is switched on, you're going to directly jump to this B2. So this switch case is equivalent to just jumping to B2 because you know this value already, and this is 2. So this switch always jump to B2 here. So you replace this entire switch case with B2. Similarly, if you are having a 482, for example, then you're going to just jump to B1 because it is the default case, and 482 is neither 2 nor 3. So you're going to just B1 in this case. So the first thing to do is implement such simplified CFG's optimizations, sub-optimization that is about constant propagation. And let's see other examples as well. Let's see empty. Now you can see that you can now see that in the full function, you can see that this B3 is an empty. This B3 is empty. It is just returning a value. It doesn't define a finite. It doesn't define instruction register. It doesn't define registers at all. It just returns a rhythm. So the optimizer can see that, at this point of time, we can just skipping to jump to B3 and return 37 directly. So maybe it is possible that this jumping instruction is replaced with this return instruction. Return 37 directly. And maybe at the later stage of optimizations, we can remove this B3 at all because this is never reached from the beginning, the initial block of this function. But for the purpose of this empty case, we can just replace this jumping to B3 with a return. Let's see another example here. In this example, you can see that what's the difference? Okay. In this example, we can see that in this branch expression, you're going to jump to B2. But B2 is directly jumping to B3. So maybe you can bypass this jumping and replace this B2 with B3 here, because B2 is empty. And yeah, this is basically the empty block optimization inside the simplified CFG optimization. You can see the difference between these two functions. So here we are replacing the entire exit with the next block's exit. But in this example, we are replacing a jump with another jump here. So you need to, so even though jumping to B2 is not the entire block exit, you can replace this jumping to B2 with jumping to B3 because block B2 is consisting of only a jump. It doesn't have finals, it doesn't have instruction, but it just jumped to B3. If it were returning a value, we should have not been able to replace this B2 with return because it is not syntactically a valid code. Only if this is a jump, we could replace this B2 with B3 here. Okay, this is the second sub-optimization, which is empty. And let's look at the merge one. Here is the two blocks, B0 and B1. And B0 is jumping to B1, and B1 is jumped to by only one block, which is B0. So there's no block that jumps to B1 except for B0. If it is the case, we can just merge two blocks like this. So we're going to merge and put the instructions together inside this B0 block. So, but before explaining the translation, let's see what happens here. Block B0 is jumping to B1 with two block arguments for finals. It is 42 and 37. And in block 1, we have two finals that is getting assigned with 42 and 37 when it is jumped from B0. And we are going to calculate the addition of these two variables and assign it to instruction register, and you're going to return it. Now, you can merge these two blocks into this, which is adding two values as well, but the registers, the final registers, were replaced with the argument here. So it is adding 42 and 37 directly instead of using a final register as described here. So the moral of the story is that when you merge two blocks, the finals should be replaced with the final parameters should be replaced with these arguments that is given to the block. So that so as a result, we could merge these two blocks into these instructions. Okay, let's move on to the last sub-optimization, which is unreachability. In this program, we're going to start from B0, and from the B0, we're going to jump to the B1, and B1 is jumping to B0. So it is basically an infinite loop. But the funny thing about this program is that B2 is jumping to B3, and B3 is jumping back to B2. But this is never reachable from the beginning of the execution because B0 reaches only to B1, and B1 only reaches to B0, and they collectively cannot enter B2 or B3. And as a result, we can remove them all together and leaving B0 and B1 only. So this is the result of such a translation. So B2 and B3 are unreachable, so we are going to delete it. So, okay, these are the four flavors of sub-optimizations inside the simplified CFG optimization. And we are asking you to implement such a translation from input to output. Okay, now let's look at the code a little bit. Let's look at the simplified CFG code, which I implemented. So many of the code are already inside the skeleton code, but what is not already implemented inside the skeleton code is the actual content of this optimization. And let's see what happens here. So we are implement what is called the optimization, and it is returning a boolean, and this boolean is indicating whether you transformed the given IR or not. If this optimization changes the IR, then it's going to return true, and otherwise it is going to return a false because it indicates whether it is changed or not. And in this const prob optimization, you're going to iterate through all the blocks here, and for each block, you're going to simplify the block's exits. And if it is simplified, then it is replaced and it is returning true. Otherwise, it is returning false, leaving the block exit as is. And you're going to do it for all the blocks. And at the end of the day, you're going to see whether at least one of them is changed in the translation. And if it is so, it is returning true. Otherwise, it is returning false. So we use this fault function for a Rust iterator. And if you're interested in how to use this, I refer you to the Rust iterators documentation, which is quite good. I mean, if you're going to deal with multiple objects in your code base, then you're going to want to use this iterator, which is very useful and which is quite extensively developed inside the standard library. So I strongly recommend you to use this. Okay, now let's see how the simplify block access is implemented. Okay, here it is like this. Okay. So it is the constant propagations simplify block exit function, which is given in a block exit, and it checks whether it is a conditional jump or a switch. Otherwise, it is not subject to a simplification. Or we can only simplify a conditional jump and switch. And this is checking whether the branches are the same. If the true branch and else branch are the same, then we're just going to return it as a simple jump because we don't need to do a conditional branch for this case. And otherwise, we're going to see if the value, the condition value here is a constant. And if it is false, then we are going to replace the entire block exit with a plain jump to the else branch. And otherwise, if it is always true, then we are going to replace the entire block exit with entire conditional branch into this plain jump to the then branch. So this is basically what is done in this function. And we are going to do the similar thing for switch cases. If everything is going to jump to the same block with the same argument, we are going to just replace it with the plain jump. And otherwise, we are going to get the constant value. And if it is constant, actually, then we are going to find the right case for the constant value and use it, replace the entire block exit with a plain jump to the right corresponding BID and block arguments. So this is basically what is done for this constant prop. And here are other optimizations as well. For simplified CFG reachability check, we're going to make a control flow graph out of this. And for this, we implemented a function that is iterating through the control flow graph, and which is collecting the control flow graph out of function definition. And using this function definition, we implemented what is this? It is it should be DFS or BFS. I don't know. It is probably DFS because we are using a vector and we are pushing and popping at the tail of this data structure. But anyway, we are going to visit. I'm going to do a search algorithm and graph color the entire graph, and only retain those blocks that is reached from the initial block. And we're going to return whether there are a block that was removed. If it is so, we changed something. Otherwise, we changed nothing. Okay, in simplify merge, we are going to make the CFG as well as previously. And we are going to calculate the integers of each block. Because we are going to do this. We are going to see if B0 jumps to B1 and no one else is jumping to B1, then we are going to merge B0 and B1. So in order to check whether it is the case or not, we are going to calculate the integers of every entries inside the graph. So please remember this pattern of hash map in Rust. So it is very useful. So please search for entry API for HashMap, which is very useful for using HashMap. And now, after calculating the integers of each block, we're going to try to replace the things here. If a block is jumping to another block, and the another block is has the integer of 1, then we are going to merge these two blocks. First, we are going to gather the information on the finals. So recall from the merge example that we need to replace these final registers with this final arguments. So we need to gather such a replacement information. For example, this B1's P0 should be replaced with 42, and B1's P1 should be replaced with 37. And we move the instructions of this B1 to B0. B1's instruction is moved to B1 here. And we are going to replace the block exit of this with this because this is jumping to B1 and it is no longer present in the optimized IR. And in the optimized IR, we are going to directly do this, which is in this case returning a value here. And so far we did until this. And after that, we are going to replace the values here. So this is replaced with these values. This is replaced with this value. And now this B1's I0 should also be replaced with, for example, say B0's I0 because it is renamed. So this instruction is moved to here. And this instruction register should also be renamed to B0's I0 in this case. So we already gathered this information at this line. And using this line, we walk the code and replaces, recursively replaces the registers with the another register. And now we remove the function, remove the block, so we change the result. So we are going to assign the result with true. And we iterate through all the blocks, all the jumps, and yeah, that's basically everything about this function. The last thing to do is this empty optimization. So it is very similar. We are going to gather empty blocks, and using this information on the empty blocks, we are going to simplify the block exits. And here, if it is a jump, it is jumping to a block, and the block is an empty block, then we are going to replace the exit with the next empty blocks exit, as we saw in the example. And otherwise, we are going to see if the case that if we are going to look into every jump argument. For example, if there is a code like this, code like branch conditional value and B1 and arguments, B2 and arguments. Let's simplify each block jump argument like this in this function. And first, we're going to see if the target block is an empty, and if it is the case, we are going to replace the jump argument with the jump argument with the empty blocks jump target. So this is exactly what you saw in the example. So we implement these two logics. If it is jump, we are trying more to replace the replace out the empty blocks, and otherwise we are mindly trying to place the empty blocks out. And that is basically that is basically everything about this translation. And I hope this video is helpful for you to start working on homework 3 and hopefully finishing homework 3 based on this video.